Okay, crisis averted. All right, here's a problem we're gonna do. I gave you the KSP. This is for the barium carbonate. I need to make myself a checklist to press record. That's what I'm gonna do. You can't see it. Hold on. Hold on. Here it is. Here's the question. This is precipitation, right? We're asking if that will precipitate out. Remember, KSP, we're given a KSP for barium carbonate. So I'm going to cheat a little. I think Dr. Keene would write out the equation of those two adding together. I'm just going to cheat. And just to jump straight to my BaCO3 goes to, this is solid. Okay, we'll talk about that later. Ba2 plus aqueous plus CO3 2 minus aqueous.
If you didn't know like solubility rules, would you normally just do like your whole net ionic equation to figure out like what cancels and what doesn't?
Yeah, do your whole thing, and you should, when you figure out what cancel and what doesn't, and it should look like this. It might be backwards.
Yeah, when I did it, mine was backwards, but yeah, okay.
That's fine. That's the more the better way to do it, because in this question it told you that is precipitating out. The question might not do that. Like he could ask you, he could just say, oh, I'm going to combine to this thing. Well, something could precipitate, right? And we would have to figure out what the precipitate was, which is that, and go and get the KSP and do all the shenanigans we're about to do later. Okay, I wasn't muted during that. That's good. Okay, so now we're here. We have our equilibrium. I guess we didn't really need this, but so now we're essentially, what I'm asking you is, which way is this thing going to shift, right? Do you remember kind of doing that recently? And then we can notice that I can get all of my, like I can get these two amounts from those two, right? I can get the concentration of these two from these two things added together. So we'll do that. We'll figure out the concentration of barium. I hope that made sense. Okay. So first I'm going to figure out how many moles of barium I have. So I have 20.0 milliliters BaNO3 2. Okay, and I use my molarity. I didn't put an M there, but that's what that is. 0.10 molarity, or God, messed it up. Okay, we got 1,000 milliliters, 1 mole, 1 liter, 1 liter, 0.10 moles barium carbonate or nitrate. So 3, 2, it's N. And then fortunately, for every 1 mole of barium nitrate, I get 1 mole of barium 2+. All right, I'm doing this step just to build good habits, so when it's not 1-to-1, I'll still do it anyway. Or I won't forget about it when it's not 1-to-1, I mean. Where's my calculator? Hold on. Is it making sense what I'm doing? Or,
Yes.
Okay, good. Okay, so I got 0.002 moles of barium, 2 plus. And then do the same thing. Oop, there goes my cap. Do the same thing for my sodium to get my moles of carbonate. Ugh. Got it. Okay, to get my moles of carbonate from my sodium carbonate. So 50 milliliters Na2CO3, 1,000 milliliters, 1 liter, blah, 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 1 liter, doing this for completion, 0.10 Na. Oh, this is moles. Moles. Na2CO3. And for every 1 mole Na2CO3, I get 1 mole of CO3 2 minus. I got 0.005 moles of CO3 2 minus, CO3 2 minus. Oof. Okay, 2 minus. Okay. So my reason for doing this, I don't know if I said, I want to compare K and Q. K versus Q, right? That'll tell me which way this thing shifts. Okay, so I'm gonna, does that make sense? I'm gonna erase all the work and keep the mole numbers. Yes. Okay. Don't need this. Keep the moles. I want to use that later. Okay, so these are moles, right? And to get K and Q, you want concentrations. So what am I going to divide this by to get my concentrations? Total volume. Yes, correct. And what's my total volume? 70 milliliters. Yes, good. Okay, so the concentration BA2 plus is 0.002 over 7, or in liters, right? 0.07 liters, so 1 mole. And same thing, similar thing for my CO3 2 minus. It's 0.005 moles over 0.070 liters. Those are numbers. We'll call that, how many sig figs do I want? I probably should have kept 3, so I'll keep 3 here. 0.0286. And I got calculated. 0.0714. Polarities. Everyone with me so far? I know that wasn't too hard. Okay. All right, now we can get Q, right? So let's find Q. So Q is my barium times 0.0286, and that is 0.0714. So Q is what? The 2.04 times 10 to the negative 3. All right, so we have, not do it because we have our 8.1 times 10 to the negative 9. Our 2.04 times 10 to the negative 3. So Q is greater, right? Q is greater than K. So are we going to have precipitate? Or is something going to precipitate? Yes, because it's shifts left. Yes, right. It shifts left, so you're making more solid. So you're going to have, yeah. Right, so there will be, your answer will be there, will be precipitate. Precipitate. Tate? I don't know. However you spell that. Make sense?
What were you saying we would have to do if it didn't tell us explicitly what the what it was?
What it was,
Mhm.
do, so I'm gonna erase this. You would have to write out your equation. So do your BA NO3 plus, and put in your states because those are aqueous. I'm being lazy here. Na2CO3. Do your thing where you get like a you switch partners essentially. So you do your we had a strong arrow, but that's okay. We'll leave that. That's fine for right now. So we switch partners. So BaCO3 plus NaNO3. I guess you could balance it, but it doesn't really matter for us. Well, you should balance it if you're figuring out your equation and stuff, just in case. So you would do and look at your precipitation, or not precipitation, your solubility rules, right? You would go back and look, and you would see that you're not really concerned with those. Both of these are aqueous because they're in a solution, so they better be. And you'll find that this one is solid and that one is aqueous. So basically, now you know that you need the KSP of this guy, you need KSP, and you need to do all this stuff for, its parts. So find the moles, the concentration of barium, concentration of CO3, and then find your Q. Did that answer your question? Got it. Cool. Okay. All right. So now go over here. We'll do another slightly different one, unless someone has a question.
You probably said this at the beginning, like before I joined, but are you doing 17 and then going into like 18 towards the end?
Yeah, I can.
Okay.
Can we do 35? I remember him highlighting that one. Yeah, we can do that. Here, let's do that. Let's see. We'll do. Hold on. Okay, I'm gonna erase this. Okay. So 35. I have it written down in here somewhere. Okay. So we have 25 milliliters. 25 milliliters. Of 0.100 molar CH3COOH. Titrating, and then we're titrating it with 0.200 molar KOH. Right. So this problem is long because there are 5. The main thing about this problem is that there are 5 parts. And so part A is part A, B, C, D, E, right? I think. Yeah. There's 5 parts, and the only part that difference is the amount of this KOH that you add. Okay. So I've done all these parts already, and the recording of them is on YouTube, so I'm not going to do all of them. I want to do C. We'll do C for titration practice. I want to do part C, but if you want to see part A, B, D, or E, I can tell you what day I did them on, and you can go watch me do them in a YouTube video, because I already did these. I did all these parts already, so we'll just do C. Sounds good. Cool. All right, so we're just going to look at C, part C. So we'll do our 10 milliliters. Okay, so we're titrating our acetic acid. Oh, I got to give you a Ka. So Ka of acetic acid is 1.8. Oop, up, camera, please. Okay, sorry, a friend was calling me. What was I doing? Oh, yeah, Ka, blah, blah, blah. We're titrating our acetic acid with KOH. Okay. Does anyone know what we do first? I'll pull this down a little.
So like I know you can do this a few different ways, because you could either do like the net ionic equation for both of them, or you could write like an equation for both of them separately.
Yeah.
So yeah.
Do you care which one? We can do
I did 2 separately, so could you do the net ionic just so I can like see it both ways, if that makes sense?
Okay, so she said write the net ionic equation, so we can do CH. So we'll write the general one. So CH3COOH plus KOH goes to, so they switch the partners, so they make CH3COOK and then plus H2O. Right, that's liquid, that's aqueous, and this is aqueous. That's one of our strong bases, remember, so that's going to break up completely. So I'm going to get, I'm just going to rewrite it right here since I don't have that much space. So I'm going to get plus K plus OH minus. This is a salt, that's going to break up completely. So CHCOO minus plus K plus H2O, that's a liquid. All right, this is aqueous. That's aqueous. That's one of our weak acids, so it's not going to break up completely. So we just leave it.
So anytime you have a strong base, it's always going to break up?
Yeah. Yeah, strong bases are going to disassociate completely, so I can do that. And then basically my K becomes a spectator ion. See, right? Shows up there and there. Get rid of it. So now I have just CH3 COH plus OH minus gives me that plus water. Cool. Okay, that makes sense. Yes. Yes. Okay. All right. Okay, now what? Does anyone know what we do next? Find the moles. Yes. Good. So we need to find the moles of these two things. I'm just going to do that quickly. Let's do, excuse me. So sorry, I was doing conversions in my head. 0.25 liters times my 0.100, and that's going to be 0.0025 moles of this guy, and then I have 0.010 liters, and then 0.010 times 0.200 equals 0.002. Did I do that math right? Okay, and then there's 0 moles of that, and I don't care about water. Okay, now we have our limiting reactant problem, right? So I do my, so that's the smallest one, so I do minus 0.0020, minus 0.0020, and plus 0.0020. I get 0 right there, 0.0005, and then 0.0020. Okay. I think I did that right, don't it? Okay, yeah. Okay, checking my math. All right, what's this? Now that we have CH3COOH and CH3CO minus floating in the same thing. What's this? What do we make? A buffer, good. And what can we do with buffers? How do we have an easy way of finding pHs of buffers? Plug it into that equation. Yes, I'm thinking when you say that equation, you're referring to your Henderson, Hasselbalch, Hasselbalch, whatever it is. Henderson something, yes. Yes. So we have the pH equals pKa plus log of our base over our acid. Oh, this is HA. And this is, so pK is the negative log of 1.8 times 10 to the negative 5th, plus the log of what? So these are usually just concentrations, but again, since I'm going to be dividing both of these by the same number, I can just put moles in there and it'll give me the same number. So the base is my CH3COOH minus, so that's 0.0020 over 0.0005, and then pH, excuse me, negative log 1.8 times 10 to the negative 5 plus log of 0.002, 0.0005. Bam. Okay, it's 5.35. Yeah, 5.35. Make sense? Cool. So yeah. Yeah, so the only other thing is just for titration is just, well, be comfortable with if that's, instead they flip, right? And if this is a base instead, like if I add a base, if I use a weak base and a strong acid instead, is the process is still basically going to be the same, except when if you get something like this, just remember that this part is your base, so this goes on top now, and that would go on bottom if this was a base, and that was its conjugate acid. And remember to put pKa, not pKb, because you'll get a Kb if that was a base. And remember to flip that to find your Ka. So there's that. So that's adding a strong acid into a weak base, and then also to remember what the about where the equivalence point is. The equivalence point is where your moles equals your acids, right? Moles acid equals moles base, right? Right. This is another important definition to remember for your titration problems. Okay. When would you do an ice table again? So you would do an ice table if you're left either with only your weak acid or only your weak base. So like in this question, 1735, part A, I was left, if I add 0, right, 0 moles of KOH, then I would just do an ice table with CH3COOH and 0.100 moles of that. Another place, I think it's part D in this question. I think it's like 12.5 right here. We had 12.5 milliliters and we get, it's the equivalence point. So we get 0 of the weak acid and 0 of the strong base. And we're just left with this weak base or the conjugate base, which is weak, right? Weak base. And then we would do an ice table with this mole amount of CH3COO minus. Just remember to change that to concentration. Right, so I divide it by my total volume, which is the 35 or 37.5, right? Or 0.0, right? Because I need in liters. Okay. So anytime you do a titration and you're left with either just the weak base or just the weak acid. I guess technically you could do it here at the buffer state. You could solve this with an ice table. Just you would drag down these two numbers as concentrations, but it's gonna, you'd have to solve a quadratic, right? And that would take you a while, maybe, unless you have a smart calculator. Answer your question. Got it. Any more questions on this? 17. No. Awesome. I guess let's try to squeeze. Let's look at one thing from 18 at least. Okay, I can't. Okay, that is fine. What is that from here? Okay, all right. Gave myself some landmarks, nice. All right, we're gonna review entropy, so get ready. I'm gonna erase this. Where's my eraser? Here it is. Okay. Which one of these do I want to do? Let's do. Hold on. We'll do a simple one. Why not? Let's do this nice and easy. H2 gas 2H. I want to know if the change in entropy is positive or negative. I got nothing. Okay. Same. That's fine. It was basically just kind of one of those things where we said that if entropy is like the amount of disorder you can have, or like the number of different states, like one thing considered. So we just listed some things where you increase entropies. We said there are some, let's see, increase entropy. So we listed some things where you increase entropy, so capital S. And so we said going from a solid or a liquid to gas, going from a solid to a liquid, right? Molecules can move around more. And then I think we said at one point the increase in numbers of gas. 1s. I think. Where did I put? Oh, that's over there. So now that I said that, what do you think? Yes, positive. Good, right. Gases, number of gas goes up. My entropy increases. Okay, good. Let's do. Oh, let's just do here. We'll do another easy one. We'll go. Let's do this. Well, that one. So entropy going to increase or decrease? Negative. It's phase change, so plus negative. Yes, negative. So yeah, careful. I said phase change, but I said going from a solid to a liquid, or solid to liquid, or from solid to liquid to gas, right? And this is going backwards, right? I did say phase change. You're right. I meant phase change going this way. If I go the other way, it's negative. So delta S is negative. You can also think about entropy is about how you can rearrange yourself, right? If you can exist in a lot of different states, right? These gas molecules can move a lot, right? They can be anywhere inside your container, inside your room. While these water molecules are more restricted, right? They don't get as much freedom as these gas ones. So going from gas to liquid, I lose some ways to orient myself, if that makes sense, kind of. I lose some disorder that my system can have, right? It's not as crazy. Bam, okay, that's that. That makes sense? Yes, awesome. Okay, let's do, here, let me ask you this. I don't have it written down. I just want to erase this. Okay, I'm going to give you, ooh, excuse me. What am I going to give you? I'm going to give you delta H and delta S. Okay, so I'm going to say delta H is negative 126 kilojoules per mole. Delta S is 84 joules per mole Kelvin. Okay. Okay, so let's do two things. Let's first, I should have written it in a corner. I don't know why. I'm gonna put it up here. First thing, let's do kilojoules per mole. Delta S is the 84 moles Kelvin per joules. Okay, first thing we'll do is we'll use, I think it's the second law of thermodynamics, right? The one that says that the S of the universe has to be positive, delta S universe, which equals delta S reaction plus delta S surroundings has to be greater than 0. Yes, yeah, okay. So we'll use that to see if this thing is spontaneous. And then we'll ask some questions. We'll look at delta G as well. So let's do this first. We already have the delta S of the reaction. Nice. That's good. It's right there. He'll give this part to you, so he'll say, okay, you'll have an equation that says delta S of your surroundings is negative delta H over your temperature. I'm gonna say I'm doing this at steady standard states. Okay, right, those circles mean I'm at 25 degrees Celsius. Okay. Okay. So I'll plug in my numbers. I'm gonna convert this to H to joules, so I have it in the right units. So negative 126 times 10 to the third joules per mole over 298, right? 0.515 Kelvin. And so my delta S surroundings, I always forget the extra S, SURR, is what? Negative 126 times 10 to negative 3, or not negative 3, positive 3, over 298.5, and you get 6 extra one. I'll do 423 joules per mole Kelvin. Right. And with that, I can get my delta S of the universe is 84 joules per mole Kelvin plus 423 joules per mole Kelvin. So this is going to be what? 705 moles Kelvin per joule. Bam, and that's greater than 0, so it is spontaneous. That makes sense? Yes. Any questions on that? I did it kind of quickly. I didn't think, I thought it was mostly straightforward. It's just plug and chug. Okay. All right, another question for you. Here, let me give you delta G. So delta G remember, is my H delta H minus T delta S. Okay, so that might help you with this question. So here's what I'm gonna ask. When is this reaction spontaneous? Spontaneous, right? And when I say when, I mean at what temperatures? And basically for this answer, I'm looking for this question, I'm looking for either always, never, high temps, or low temps. Right, those are your, here, I can write that better. Those are your the answers I'm looking for. Always, never, always, never, low temps, high temps, low temp, high temp. High, always, because delta H is negative and delta S is positive. Yes, good. Yes, always. Right, good job. So yeah, you're looking, so remember you want for spontaneity, so for spontaneous, you want delta G to be less than 0. So since delta H is negative, delta S is positive, and T is always positive. T is always going to be positive because it's in Kelvin. This is always negative, no matter what. Since this is negative, that's positive. This is always negative, no matter what, always. So good. Okay. Do any of that make sense? Got it. Cool. Awesome. I think there's a homework question to ask you. So that gives you delta H and delta S, and then asks you this, kind of. I think they have an extra option. I forget what the first one is. So it's like something about delta G. I don't remember.
But I have a question.
Yes.
If delta H is positive and S is positive, then that'll be delta G would be positive?
Well, it depends, right? So if this is positive and that's positive, then if this quantity is bigger than H, if that is greater than H, right? Then delta G is negative, right? Do you see what I'm saying?
Yeah, like what if you don't know, if that makes sense?
So
like if you don't know what the sign is on T and delta S being multiplied together?
So if if you don't know the sign,
like if you don't know if T times delta S is like positive or negative?
well, if you know delta S, the sign of delta S is always a sign because T is always positive because it's Kelvin and Kelvin never becomes negative. So whatever the sign of S is a sign of that. And so if you got a situation like this, this is your high temperature, right? This is your high temperature option. Let me do it a different way. That's this one. Because if if this quantity gets bigger than that one, then delta G becomes negative. So you need a high enough temperature. You have like this temperature where G is 0, and then anything above that temperature is spontaneous. And anything below it is not spontaneous. Did that answer your question? Yes, good. Cool. Anything else?
Really quick, can you just run down everything from chapter 17? Because I'm like kind of all over the place with that chapter because we went through it so fast. So just like the concepts,
Yeah.
or like what we should study for the quiz on Tuesday.
Here, let me put the sign in link in the thing just in case people want to leave and they haven't signed in yet. Here, go sign in if you haven't yet, and then we'll do chapter 17. Okay, let's see. I'm gonna erase all this stuff. Okay, so chapter 17. Chapter 17. What do we have? So this was basically, so first, excuse me. The first thing we talked about was solubility. Solubility, right? So that had to do with KSP. So KSP, and you had some salt, barium. I'm thinking. So you had something like, I don't know. I'm assuming we're gonna guess that barium chloride, BaCl2. No, let's do something. We'll stick with barium carbonate. Okay, so here's our thing, something unsolid, Ba2 plus CO3 minus. So we had our little ice table here. I'm doing this for a reason. Oh, what is this called? Do you remember what the name of that is? Why is it SP?
Is it about molar solubility?
Almost. Molar solubility is here. I was thinking solubility product. Right, you got the solubility part. That's pretty good. Yeah, so solubility product. Don't remember that KSP is a solubility product, so you can use those interchangeably. So we had our ice table. Don't care about this because it's solid. Usually these are 0. Usually, right? 0 plus S plus S. And this became S and S, whatever's. And then these are your molar solubility. That's molar solubility.
And that's what you're usually solving for in those kinds of problems, right?
Yeah, usually you're solving, molar solubility. You can use molar solubility to get regular solubility. Like grams per liter instead of moles per liter. Sometimes some questions give you the molar solubility, and they ask you for the KSP. So usually it's one or the other. What else? We also had the do's. So so you had and you also had the does something precipitate. Questions where it's basically like a K versus Q thing. K versus Q is does precipitate. Also, don't forget, I could ask you, does barium carbonate precipitate in a solution in a barium nitrate solution, right? So I say I have, I don't know, in a 0.2 something molar, right? So if I gave you like a solution it was sitting in, so I added some, let's say I add some 0.200 molar barium nitrate, right? If I add this to that solution, I put the 0.200 right there, right? Because it's the barium from this, this is gonna dissociate, and this barium is gonna go into my ice table. So there are questions like that, and then you again ask about molar solubility, or how much of that dissolves, or stuff like that. What else? I think that was it for the solubility questions. Yeah. When do you use moles? Like, when do you use moles?
Like in the problem before where we like set up kind of like an ice table and we used those. Like I don't know when to do that and when not to.
So we did that because we were adding two things. So I was saying I was adding some volume of this. So I had like 10 milliliters of that, and then I was adding it to 3 something of what was it? It was like sodium carbonate. Right. I was adding these two things together. I was mixing them at 20 milliliters. So again, I still have this ice table going on in there, but now I need to get moles of these two things, of CO3 and BA, because I'm diluting both of these, right? So if I just add this, if I added, basically it's because I'm diluting it, right? I'm diluting it by mixing these two things together, right? It's not going to stay at that same concentration again. So if you add two things together, if you're adding two things with two different volumes, you have to go to moles and divide your moles by the volume to get your new concentrations.
Is there a difference between that problem and a titration problem? Besides, like, the titration problems will say titrated, right?
So the difference is, it's the only difference I think is that titrations involve acids and bases. I'm think, or no. So, and also that both of these, phone, please. Is it broken? Anyway, I can still talk. The titration problems still have acids and deal with acids and bases, but my I lost my train of thought. And my acids in my titrations, my weak acids don't totally disassociate. In these problems, both of my reactants completely disassociate, so we can do our net ionic and we can cancel some things out. Does that answer your question? Okay, it's back. Got it. Okay. Trying to think, was there anything else? I think that was all with solubility stuff. We had buffers, but yeah, so then we talked about buffers, right? So for buffers, so what's a buffer? The question.
A solution that contains a conjugate pair.
Yeah, a weak conjugate pair, right? It can't be so a weak acid and its conjugate base, or a weak base and its conjugate acid. Oh, let's see. And okay, so we have, and you have a ratio of your acids and bases. Does anyone remember? There's like a limit on this. Does anyone remember that from the video? It's okay if you don't. Yeah, 0.1 to 10. Cool. Right. Okay, so that's our ratio that we have to have in order to get a buffer, and they resist pH change, right? Yes, I don't know if he's asking conceptual question, but they resist pH change. It's the main point of buffers. And basically we boil it down to finding the pH to pH equals pKa plus the log of our acid over our base over our acid, sorry. Base over acid. That's, so the questions could be, what's the pH of a certain buffer, or how to design a buffer that maintains a pH of around whatever, right? Whatever number. The key to that is you want to pick, so when you're designing buffers, you want to pick the whatever acid you pick, you ideally want the pKa to be the closest to your pH. So if I said I wanted a buffer of 3.72, that's where the pH stayed around. And I had two acids to choose from. I had something with a pK of 3.62 or 2.13. Right, I would want to pick this one. Pick this. These are pKs. So I basically want to choose that one because it's closest to the pH I want. And then I do my math and figure out what kind of ratio I need. Excuse me. Okay, so that was buffers. That's part we did in 17. And then titrations finally. Titrations. Okay, I can either do a strong acid, strong base, weak acid, strong base, or weak base, strong acid. Right, those are the three types of titrations that I could do. Okay. So for this one is the pH at the equivalence point. So I'm going to relate all the pHs of their equivalence points to 7. So pH 7, pH 7. This may be something he doesn't ask you, but we're going to talk about it just in case. This one he'll probably ask, what's the pH of a strong acid, strong base at the equivalence point? This is at equivalence point. Strong acid, strong base, I'm at the equivalence point. How does my pH relate to 7? Does anyone remember? Equal, correct. It's equal to 7. So yeah, that's just because when they're equal, both of these neutralize each other, so both of these go away, and their conjugate parts aren't strong enough to induce a pH. So you just basically get left with water and salt, and so the pH is 7. Okay, this one. So this is gonna be harder, maybe. You're smart people, you can do it. The weak acid and strong base, my pH at the equivalence point, how is it gonna relate to 7? Does anyone know? Greater than 7, good, yes. Greater than 7, right? You can either think, oh, the strong base is, since this is a strong base, it's pulling it more toward, pulling the equivalence point more towards the basic side. Or you could think, oh, since when I neutralize both of these, I get left with the conjugate base of that, and that makes my pH. Whichever one works for you. I don't know which one's more correct, but that's how I think about it. So this one, by flipping it, is the other way. Great. It's less sand. Again, either the strong acid's pulling the equivalence point more towards the bottom, more towards the acidic side, or when I neutralize both of these, I get left with some of this conjugate acid, and so that makes my pH acidic. Bam. And then all the stuff, the titration math. I'm trying to think, anything else conceptual? I don't think so. I think that's all I can think of for like conceptual ideas anyway. Does that help sum up 17? Got it, thank you. No problem. Are there any other questions people have? I know it's a little over, but I'll answer any questions if you have them. Thank you. You're welcome. You're welcome. Thanks for coming, everyone. Did you sign in? Did all of you sign in? Hopefully. Yes. Cool. All right. Thanks. All right. No problem. I'm glad all of you find this helpful. Still trying to get the hang of doing online stuff. All right. Well, if you guys are good, we can be done. It's after 9. But again, if you have any more questions, I'd be happy to answer them. All right. See you later.